There might actually be a way to create a warp drive, though the idea exists at the farthest edge of physics, territory so abstract and complex that it borders on the impossible. According to the laws of relativity, nothing can travel faster than light. Yet while matter itself cannot surpass that universal limit, the very fabric of space can. That simple but profound distinction became the foundation for one of the most astonishing announcements in modern history. When NASA revealed that it had developed a propulsion system capable of reaching light speed, at least in controlled, limited conditions, the news sent shockwaves through the scientific world and beyond. For decades, NASA had been known for incredible achievements, landing on the moon, exploring Mars, and peering into the cosmos with the James Webb Space Telescope. But this revelation surpassed them all. The press briefing had been kept under the strictest secrecy until the final moment. Inside a secure conference room, senior researchers disclosed that after decades of theoretical work, propulsion experiments, and classified research, NASA's team had successfully developed a propulsion system so advanced it could, in theory and now in limited practice, achieve light-speed travel. The revelation was not made lightly. It carried with it a sense of disbelief, awe, and a humbling realization that humanity might have just stepped beyond the final frontier of what was thought possible. For generations, the idea of moving at the speed of light had belonged solely to the realm of science fiction. Einstein's theory of relativity defined it as an insurmountable cosmic boundary. Anything with mass would require infinite energy to reach it. But NASA's new breakthrough was said to bypass this law, not by brute force, but by manipulating the structure of space itself. The engineers and physicists involved described their invention as a field-based warp mechanism inspired by the Alcubierre drive hypothesis of the 1990s. Unlike a traditional engine that propels a craft through space, this system worked by bending space-time around the vessel, compressing space ahead and expanding it behind. The result was not motion in the traditional sense, but displacement without movement, travel that redefined what motion meant. For decades, such theories had existed only as mathematical concepts. No one had ever expected them to manifest as a functioning engine. What made it possible was NASA's foray into quantum vacuum engineering. Through years of experiments, researchers studying the Casimir effect noticed strange anomalies, tiny fluctuations of energy within the quantum vacuum that seemed harnessable under extreme precision. By manipulating fields of negative energy density, once considered purely hypothetical, they learned how to create localized distortions in space-time. Even more astonishingly, these distortions could move and be controlled. The first demonstration of the technology took place under intense secrecy at one of NASA's remote facilities. The craft involved wasn't large, only slightly bigger than a probe, but it housed a containment ring powered by a field generator capable of manipulating vacuum energy at a microscopic level. When activated, the sensors recorded something impossible. The vessel shifted a measurable distance, not through acceleration, but by instantaneous displacement. Every propulsion model known to science relies on reaction and thrust, one thing pushing against another. But this engine didn't push, it warped. The results were verified over and over until there was no room left for error. Only then did NASA begin work on a larger prototype. As whispers spread through scientific circles, rumors began to surface about a mysterious Project Genesis, a classified initiative that had reportedly been operating quietly for over a decade. Funding for the project had been funneled through various sub-programs under the guise of quantum field analysis and high-energy propulsion studies. The secrecy wasn't born from paranoia, but necessity. If the research failed, it could have crippled NASA's credibility for decades. But it didn't fail. Against all odds, the impossible became real. At the heart of the new propulsion system was what NASA called the Quantum Flux Field Drive, or QFD. Unlike any conventional engine, it didn't expel fuel or rely on combustion. Instead, it manipulated quantum fields to create a warp bubble around the craft, separating it from the normal laws of inertia and relativity. Inside this bubble, time remained constant for the vessel, while space outside it bent and contracted. To an outside observer, the ship appeared to vanish from one point and reappear at another almost instantly. The power requirements, once thought to be infinite, had been drastically reduced thanks to new energy conversion methods that harnessed zero-point field fluctuations. For the first time, the notion of infinite energy demands no longer applied. The implications were staggering. Humanity had always been imprisoned by distance. Even our nearest star, Proxima Centauri, lies more than 4 light-years away, an impossible journey with current technology. But with light speed or near light speed travel, what once took millennia could be done in days or weeks. Exploration would no longer be limited to our solar system but extended across the stars. For NASA, it wasn't just about reaching other worlds. It was about redefining humanity's place in the cosmos. The announcement, though measured, carried immense emotional weight. NASA's administrator, joined by top physicists and engineers, explained that while the Lightspeed test had been successful, human travel was still far from reality. The prototype had been unmanned, remotely controlled, and rigorously monitored. Even so, the sense of triumph was overwhelming. For the first time in history, humanity had glimpsed the true scale of its potential. Within NASA's corridors, the mood was electric. Scientists who had dedicated their lives to propulsion theory watched their ideas come alive. Engineers began sketching out designs for future missions, interstellar probes, deep space research vessels, even frameworks for manned expeditions beyond the solar system. The dream of reaching exoplanets no longer belonged to fantasy. It had entered the realm of logistics. The line between imagination and reality had begun to blur into something extraordinary. To understand the significance of this achievement, one must imagine what it means for humanity. Space, once an infinite ocean too vast to cross, had always humbled us. For millennia, people looked up at the stars and wondered if they were forever out of reach. Every leap in technology, from steam engines to rockets, had been driven by a desire to escape gravity and touch the unknown. Now that unknown was no longer unreachable. Humanity had found a way to bend the very structure of the universe itself. Inside NASA's laboratories, the atmosphere was one of focused wonder. Researchers dove deep into the physics that made the breakthrough possible. The quantum flux field was discovered to create gradients between positive and negative energy densities, generating waves of space-time compression. The ship didn't technically move faster than light. It moved differently. Within its field, light itself followed a curved path, allowing the vessel to cover immense distances instantaneously relative to the outside world. The very concept of velocity lost meaning. This wasn't just faster travel, it was a reinvention of motion itself. Physicists who once swore by Einstein's cosmic speed limit began reevaluating the boundaries of relativity. The old equations still held true, but within the QFD bubble, new variables emerged. Space-time was no longer rigid and linear. It was flexible and responsive. The craft didn't fly through space. It rode waves of geometry, surfing the contours of the universe like a ripple across water. For the first time, a human-made object wasn't merely flying, it was bending reality.